Okay, good morning, everybody. I hope you guys can hear me. Good morning, Rasul. So before we talk about physics today, I thought we should go over a few things that popped up in Canvas since Friday. So the first thing I wanted to point out was that we've posted office hours now, so that this is the best place to go if you have homework questions, because it's always easier to explain physics problems one-on-one, or at least where you can like write things on a whiteboard and you can tell us where you're stuck and we can help you. It's much better to do something like that in office hours than to try and do it via a discussion board. So, my office hours will be Monday, Wednesday, 1:30 to 2:30, and then you can see all the TA office hours there. Okay, so I think I did show you that on Friday, but just a reminder that they start today. Okay, and then the other thing I wanted to mention that some of you have already noticed is that our first written assignment is available. Okay, and the way this one works is that you submit part of it through Canvas and part of it through CrowdMark. Okay, and this is due on Friday at 11:59 p.m. So you submit your numerical answer with no units, just the number, and follow the instructions for how many decimal places. So you enter a single number in the Canvas quiz, and you can enter as many times as you want until the deadline. And then you submit your written work, which should match your number. Okay, you should submit your written work via CrowdMark, and that's also due Friday at 11:59 p.m. And you should have received your CrowdMark instructions via your SFU email. Everything's going to go through your SFU email, so please make sure that that's the email that you're checking for work, for things related to this class. Okay, so I don't know if anyone has any questions about any of that. If not, we're going to go ahead and do some physics. So let's see if I can find my PowerPoint. There's my PowerPoint. Okay, and we will start the PowerPoint going. There we go. All right, so instead of a comic today, I wanted to start with something else I posted in Canvas. I did post also, you might have noticed, some study skills, study hints documents. And one of those things I posted is this little poster, which is all about growth mindset, which is something you may have heard before. I think it's a really good way to approach physics, is with a growth mindset. Okay, with realizing that it's a tricky, difficult subject, and that to get good at it, you have to practice. So like it says, you can always improve. It may take time. You may have to try multiple different strategies to figure out how to do things. Making mistakes is not a bad thing. Making mistakes is how you learn. Okay, so that's one thing I really hope you guys keep in mind, that anybody can do physics. It just takes a bit of work to become successful at it. Okay, and actually one other thing I forgot to mention is that if you are looking for someone to help you with your physics homework, apart from me or the TAs, there's also the Science and Math Peer Tutoring starts today, and there's a link to the Science and Math Peer Tutoring website in Canvas as well. I'll show you that one at the end. Okay, so what are we going to talk about today? We are going to talk about vectors. Okay, so we'll start really quickly with the definition of a vector. So I'm going to sort of go over a little bit some of the things in the pre-lecture videos. So as you saw in the pre-lecture videos, a vector is a quantity that has both a magnitude, size, and a direction. And you can sort of picture a vector as an arrow. All right, so here's the vector A, okay, drawn as an arrow. We often draw them on an XY coordinate system. We don't have to, but it's useful to draw them on an XY coordinate system like this. Okay, and when you talk about a vector and you want to write it down, you want to write the name of the vector, in this case A, with an arrow over the top. That's really important to indicate that you're talking about a vector quantity. Okay, and to define or describe a vector, you need two things. You need the magnitude, or how long the vector is, and you can either write that as A without an arrow on top, or you can write it as A with an arrow on top, and then you put your absolute value signs on either side of the A. Okay, so that's two different ways to write the magnitude or the length of a vector. All right, and you'll see when I go through things, I'm very careful about when something's a vector, it will have an arrow over the top, and when something's a magnitude, it will not have an arrow over the top. And then the other thing you need to know is the direction. Okay, which way is the vector pointing? Okay, and we're going to try and be very careful in this class about not just giving an angle. So here we have the angle theta, okay, but not just giving the angle, but saying where the angle is. Okay, so in this case, this angle theta is above the positive x-axis. Okay, I could have chosen a different angle. I could have chosen the angle from the y-axis and said I have an angle 90 minus theta to the right of the y-axis. You could have done something like that. Either one of those would be fine. You just have to be careful and make sure you specify exactly where your angle is. Okay, and we're going to try and avoid using north, south, east, west unless the problem gives you as directions north, south, east, west. Okay, where typically if they don't give you directions, then you want to draw your own coordinate system, your own xy coordinate system, and then use that, and then use x and y for your directions. So there's a lot of quantities in physics that are vectors. Some of them we've run into already: displacement, velocity, acceleration. One that we're going to run into soon is force, very important quantity in physics, which is basically what causes accelerations. So, and then as we'll see as we go through, there's lots of other vector quantities in physics. So, another way to specify a vector, instead of using a magnitude and an angle, is to use what we call components. And for components, you do need to define a coordinate system, or Cartesian coordinate system. Like in our case, in 2 dimensions, we have an xy axis, which are perpendicular to each other. So in that case, you can talk about the x component, say of our vector A, ax, as being how far along the x-axis your vector points, and the y component, ay, as being how far along the y-axis your vector points. And if you know, if it's a 2-dimensional vector and you know those two quantities, that completely specifies your vector. It tells you exactly how long it is and where it points. So you can figure out what those two are if you know the magnitude and the angle of a vector with using our trigonometry that you probably learned in high school. So in this case, the x component, right, would be the magnitude of the vector A times the cosine of the angle, because that's the adjacent side there. And the y component would be A sine theta, because that's the side that's opposite the angle. So and hopefully you remember your trigonometry. If you don't, that's a good thing to review. We use a ton of trigonometry in physics. Trigonometry and geometry too. So if you want to figure out, say you have the components, ax and ay, and you want to know what's the magnitude and what's the angle, then you can use the Pythagorean theorem. Basically, one leg of the right triangle squared, ax squared, plus the other leg, ay squared, and take the square root, and that gives you the hypotenuse, or the magnitude of the vector. And you can get the angle theta from the tangent. Basically, tangent of theta is the y component over the x component, so theta is the inverse tangent of ay over ax. Now, I'm hoping this is not all completely brand new to you, but it's stuff that you want to be really good at dealing with, because we're going to use it over and over semester, over and over, even more so in Physics 102. So it's important that we all have a really good understanding of vectors. All right, so One thing to be careful with is the signs of components, okay? And what will you choose to use, okay? So you can see here, we have our vector A again, and the vector A on the left has a positive x component and a positive y component, but the vector on the right here, okay, has a negative x component because it points towards the negative x-axis, but it has a positive y component, okay? So you have to be careful when you're calculating your components. So in the first case, we just use those two equations I wrote down before, that ax is a times the cosine of theta, and ay is a times the sine of theta. But in the second case, if you're going to choose the theta, which as being the angle from the x-axis, like I drew here, if you're going to choose that to be your theta, then you actually have to explicitly put in the minus sign, okay, for ax to make it negative, okay, because a times the cosine of an angle less than 90 will be a positive quantity. So if you want your x component to be negative, then you have to explicitly put that minus sign in. But the y one doesn't need a minus sign, right, because that's a positive component. So, and that'll be true. We're gonna have vectors that point in all four quadrants here. So if you're gonna choose, always try and use that angle from the x-axis, which people like to do because then it's easy to picture the sizes of the components and which one's bigger, and so forth. Because, for example, if theta is less than 45 degrees, then the x component will be bigger than the y, the size of it, right? And if theta is bigger than 45 degrees, y will be bigger than x. Right? So, so it's nice to use that angle theta, but then you have to be careful about putting in those minus signs carefully. Okay, so I believe it's time to try a poll question. So here's a poll question. So I'm going to get the poll going while you have a look at this. All right. Oops. Okay, I'm trying to get my poll going here. I believe it lets me do 5 choices. Yes, it does. Good. Okay. So there's our poll. Okay, so the question is, if the length of the following vector is 4, what are the x and y components of this vector? And you've got your 5 choices now. Okay. Now, one thing to be careful about here is to notice that I gave you the angle not from the x-axis, but from the y-axis. And I think this is one, I mean, you can go and calculate it, but if you just think about the angle 30 degrees being less than 45 and sort of eyeball the sizes, you can probably get it without doing all the math. And that's actually a useful thing to get good at, is eyeballing sizes of components so that you can double check your work after you calculate them. You can say, oh, okay, does it make sense that the x component's bigger than the y, or vice versa? Okay, well, it looks like people have stopped responding. I think maybe we'll do like 10 more seconds here. So if you're not sure, go ahead and take a guess. Okay, people are starting to respond a bit more now. Good. Okay, I think we'll do 5 more seconds now. 5, 4, 3, 2, 1. Okay, so let's see what everybody thought. Okay, so it looks like the majority think that it's B. Okay, and a small group think that it's C. All right, so let's have a look. So how do we figure out the components when the angle is with the y-axis? Well, what happens essentially is you flip-flop your sine and your cosine. So in this case, the x component is going to be the sine of 30, and the y component will be the cosine of the angle, because the x is now opposite and the y is adjacent. And then the other difference, or the other important thing to put in is, again, we're putting in our minus sign explicitly, since we're basically pointing in the negative x direction. Our x component is going to be negative, but since the vector is pointing in the positive y direction, our y component is going to be positive. So we have a negative x and a positive y. Okay, and so there's only two answers, B and C, that have a negative x and a positive y. Right? And then the other thing to realize is that basically the sine of 30 is smaller than the cosine of 30. And so that means that our answer is B. So well done, everybody. I'm going to get to the poll now. Who voted B? Okay. And I don't know if there are any questions about that one. If not, we're going to keep going. So now we're going to talk about adding vectors, which is something that we're going to have to do a lot of as we go along, especially when we get to forces. But even when we're talking about displacements as a vector and somebody undergoing two different vector displacements. So how do we figure out that? Someone talking? I can hear somebody talking.
I'm sorry. I guess some people have questions. Their hand is up.
Someone has their hand up? Okay. Sir, what's the question?
I don't know what's the question. Their hand is up.
Oh, okay. Sometimes people do that by mistake. So I think let's just keep going unless they put the question in the chat. Okay. So how do we add these two vectors, right? How do we figure out what's A plus B? So there's two different ways to do it. One way is to basically do it pictorially. And the way that works is you start with vector A, the first vector, and then you draw vector B so that the tail of vector B is at the tip of vector A. So I just moved vector B over to a different position. I didn't change vector B, okay? Because a vector is defined by its length and its angle. It's not defined by where it's located in space, okay? So you can move vectors around. So I moved vector B so that its tail is at the tip of vector A, and then A plus B is just defined to be the sum of the two vectors there, and it's the vector that points from the tail of A to the tip of B. Okay, so that's what A plus B looks like and how you would do it pictorially. Okay, so one thing to notice is you can do it in the opposite order. So I could have started with vector B, okay, and then drawn vector A, so moved vector A over, so the tail of vector A is at the tip of vector B. And then again, if I draw a vector that starts, remember you always start at the tail of the first one, so I start at the tail of B and go to the tip of A, and I get the vector B plus A. Okay, so, and if we look at that, okay, closely, you can see that A plus B and B plus A are in fact the same vector. They're at different locations, but they have the same length and they point in the same direction. So they are in fact the same vector. And that's always going to be true. That it doesn't matter the order you add vectors in, you will get the same result. Okay, so how about subtraction? So subtraction is a little bit trickier, but essentially, as you probably remember from adding and subtracting normal numbers, subtraction is the same as adding the negative of a number. So A minus B is just equal to A plus the negative of vector B. Okay, so what's the negative of vector B? Well, that's just a vector with the same length as vector B, but it points in the opposite direction. So here's negative B. Okay, the orange one is negative B. It's the same length as B, but it points in the opposite direction. And in fact, you can see if you were to add these two vectors together, right? If you were to take minus B and put the tail of minus B on the tip of B, you'd get back to where you started. So, and that tells you the two vectors add up to 0. Okay, so that's what negative B looks like. So if we take negative B and we put the tail of negative B on the tip of A, and we look at what's called the subtraction or the difference, A minus B, what would you do? You would draw a vector that starts from the tail of A and goes to the tip of minus B. And so that's what A minus B looks like. Okay, and it's quite different than A plus B. And now with subtraction, you do have to worry about the order. Okay, so I thought we'd try another poll question. Okay, so let's do this one here. So again, we've got 5 choices. B, C, D. Okay, so we're going to start this poll. So we have vectors A and B are shown to the right. And the question is, which of the following vectors I drew below best describes A minus B? So which one is the closest to A minus B? And remember, all you have to do is figure out what's minus B and add it to A. And oftentimes, if you can't picture it in your head, just go ahead and draw it on a piece of paper. That's always one of the best ways to figure these things out. All right, I think most everybody's had a chance to answer. Maybe 10 more seconds here on this one. So like as usual, if you're not sure, go ahead and guess. Okay, and let's do 5 more seconds. So 5, 4, 3, 2, 1, and let's look at the responses. All right, so it looks like we have a large group voting for B. Okay, and then we have a few C's and a few D's. Great, okay, so let's have a look at this and see how this would work. All right, so we're looking for A minus B. So it would look something like that. There's A, and then what I did was I flipped the direction of B, so I have minus B, and I stuck it at the end of vector A, and which one does that match best? Well, that one best matches B. So, in fact, B was the right answer. So well done to the majority of the class. So that's good. It's good to have a handle on vectors. And those of you who are still sort of getting the hang of vectors, basically just practicing with it, you'll get better at it as you go. All right. So that's how you would deal with addition and subtraction by drawing vectors. There's another way to do it, and that is to look at those components we talked about earlier. And this is a picture from your from the pre-lecture. But what I thought I would do actually, rather than, is to go and look at one of our FETs again, because there's a really nice vector addition FET. It's hopefully going to pop up for you. That looks something like this. Okay, where you can play around with vector addition. Okay, and you can play around with, like, you just choose a vector. So this is vector A, and you can stick it on the coordinate system. Say I do like that or something. Okay, and you can see up above that they tell you the magnitude. They can tell you the angle. Okay, and that's the angle from the x-axis. Okay, you can even draw it in down below. Okay, and you can actually add in the actual components and the magnitude on the picture itself. Okay, and so you can see that the x component is just how far along the x-axis you are, right? How far along it points along the x-axis, which in this case is 30, and the y component is how far it points along the y-axis. Okay, so that gives you a nice picture of a vector. And then I'm just going to turn off those values, at least for now, because now what you can do is add a second vector. Say I add vector B. Here's vector B. Okay, and say I make vector B point like that. Okay, and now you can see vector B has a positive x-axis of 10, sorry, positive x component of 10, and a negative y component, because it points downwards here, of, and that's equal to -5. So then once you've drawn your two vectors in this FET, then you can look at the sum. And all you have to do here is turn on the sum. So you go sum. Okay, and you can see what's the sum, okay, which sometimes people refer to as the resultant vector. Okay, is a vector that points from the beginning or the tail of vector A to the tip of vector B. Okay, and you can see pretty clearly here, okay, if we now put in our numbers, okay, that you can figure out the components of your sum vector S, okay, and the components of the sum vector S, okay, are just the sum of the individual components in each direction. All right, so for example, the x component of vector A is 30, and the x component of vector B was 10, so the x component of vector S is 40, this number down here. Okay, and then similarly, the y component of vector A was 17, and the y component of vector B was -5, and so the y component of the sum is just 17 minus 5, or 12. So you can see how easy it is to figure out the components of a resultant vector, the sum of two vectors, if you know the components of the two individual vectors. So when we add vectors in physics problems, we will pretty much almost always use components. So when you're given a vector quantity, usually the very first thing that you will do is figure out its components, okay? And then, especially when you're dealing with things like forces and you want to add forces, you're going to want to figure out what are those individual components for the different vectors, okay? And so this is a really nice fact. Like if you have vectors in a problem, you can go and model them in here, okay? And you can even do things like you can have 3 vectors. I'm just going to try a slightly different scenario. Let me turn off some of the values for now. But you can have vector A, and you can have vector B. Say vector B is like this. And then you can have vector C. Okay, and notice in this case, the way the PHYS does it is they call this negative angle because they're going below the x-axis and back. Okay, that's another convention you can do. And then in this case, when you look at the sum, you can see, again, that it points from the tail of the first vector to the tip of the last vector, vector C. So just like with adding 2 vectors, when you add 3 vectors, you essentially do it the same way. Okay, you draw the first vector, draw the second vector with its tail on the tip of the first one, draw the third vector with its tail on the tip of the second one, and so forth. And so you can see, for example, if I were to have the last vector point back to where I started, which would be sort of like if a person was going for a walking trip and they walked along A for a while, and then they walked along B, and then they went straight back to where they started. Say it could be a kid running on a field, or it could be an airplane following a path, okay? And you end up back where you started, and you can see that the sum, basically you can't see the sum, because in this case the sum would be 0. Because if you look at all the, you can see down here, here's S. Vector S is 0. Oops. Excuse me, I thought that was turned off. So, okay. Sorry about that. All right. So anyway, so this is a good thing to play. It's a fun thing to play around with, to have a look at how you add vectors together and how the components combine. And so here we got our vector S, where it has angles not defined, both components are 0, and so forth, and the magnitude is 0. So that's how we add vectors. So let's go back to our slideshow now. Where are we? Here we go. Okay, so there's our. So this is basically this picture in the slides, which was from your pre-lecture video, is essentially showing you the same thing, that the x component of C, which is the sum of the 2 vectors, is the sum of the 2 components, and the y component is the sum of the 2 y components. So we did that. Okay, so now we have another poll question. So I will start this one going. And while I started going, you can think about what the answer might be. And this one is another one where it might be useful to draw a picture. Okay. So you're adding 2 vectors. One is length 20 and one is length 40. And the question is, what is the only possible resultant magnitude, which is the magnitude of the sum of the 2 vectors, that you can obtain out of the following choices? So, and you've got 5 choices there. And one hint I guess I would give you for this one would be to think about what's the biggest the sum could be and what's the smallest the sum could be. Look at the two extremes. That's something mathematicians like to do, right? They like to look at the extremes. And if you're not sure, go ahead and ask a question in the chat. You guys are welcome to chat with each other. Okay, I really thought I had that turned off. It's a new phone. All right, it looks like people are still pondering this. A lot of pondering going on. All right, I think we're gonna do maybe 20 more seconds. There's a lot of people still pondering. And while you ponder for 10 more seconds, I'm gonna get rid of my phone. Okay, so now I think we should do maybe 10 more seconds. All right, 5 more seconds here. So 5, 4, 3, 2, 1. All right, so let's have a look at the responses. All right, so what do we got? We have the largest group is going for C with 103 people. And then the next biggest group is going for E. Okay. And another group for D. So there's a bit more indecision here on this one. So let's actually have a look at this so we can understand what's going on here. So let's get rid of the poll. There we go. Okay, so the answer was C. So the largest group was correct. It was C. So why is it C? Why 37? Why is that the only one possible? All right, so let's think about it. So I drew a little picture here. And remember I said it's useful to look at what's the biggest it can be and what's the smallest it can be. So let's start with the smallest possible resultant. Okay, the smallest possible resultant occurs when the vectors are in opposite directions. Okay, so the 40 unit vector here is up and the 20 unit vector is down. And when you add those two vectors together, you end up with a resultant with a length of 20. Because you take 40 minus 20, you get 20. So that's the smallest you could get. All right, so that rules out A and B. right? Because that's the smallest you can get. And then the biggest you can get would be the maximum resultant occurs when the vectors are aligned, when they point in the same direction. So then you've got, in this case, 40 up plus 20 up. And so your resultant will be 60 up. And so that's the biggest it could possibly be. You can't go beyond that. That's the largest you can get. So that rules out 64. And so that rules out choices D and E. Okay, I don't know if anyone has any questions on that. Okay, but that's what it looks like. Okay. You know what? I think I just realized that, and I'm going to apologize. I think I might have forgot to turn on the chat. And I just realized at the end, I'm really sorry. I completely forgot. So I just turned it on. Okay, so Ryan, you have a question. Oh, we got lots of hands risen now. I apologize. I had no idea the chat wasn't turned on. I'm really, really sorry. It's this stupid, when the class gets bigger than 250, I have to use a special setting, and the special setting doesn't include a chat by default. So I'm sorry about that. So does anyone have any pent-up questions right now? Okay. Oh, someone was calling me. You were calling me. How did you know my phone number? Anyway, so okay, apologize. I'm not sure how you guys got my cell phone number. Okay, so a resultant vector of minus 20 has the magnitude of 20, right? Okay, so that would be, we were talking about the magnitude there, right? Okay, let's go back to our slide now. Now I understand why you guys are being so quiet. I understand now. I apologize. These things are going to happen. Okay, we were talking about the only possible resultant magnitude. Okay, so yes, if you had a vector 20 up and a 40 down, okay, then you'd end up with a 20 down, but that would still have a magnitude of 20. Okay, so yes, the answer here is 37. Okay, so so anyway, you guys, and I still don't know how you got my phone number, but anyway, okay, so you know what? Next time, if the chat's not working, I'll just have to try and pay better attention. I'm sorry about that. All right, so let's finish up by looking at the vector quantities that we're going to be using for this, basically for this chapter. Okay, so we are going to be often looking at displacement here. And so here's a picture of a displacement vector where, say, for example, you had somebody who started at position x1, y1, and they moved to position x2, y2. Okay, and so you can see they underwent a displacement delta x in the x direction and a displacement delta y in the y direction. Okay, and that ultimately results in what you might call a displacement vector, delta r, okay, whose components are delta x and delta y, and it points from the starting position to the ending position. So in 2 dimensions, you can see, just like in 1 dimension, our displacements had a sign. It was either positive or negative, right? Now our displacements will be vectors, okay, and the component of those vectors, okay, will be the 2 separate displacements in the 2 separate directions, okay? All right, so here's another picture of the same thing, okay? So now what we've done is actually define the positions as vectors, okay? So we have a position vector R1, okay, which is basically is your initial position, and position vector R1 has an x component x1 and a y component y1, all right? And then we have a position vector R2, which has an x component x2 and a y component y2. Okay, so the components are just the individual positions along the 2 axes, and then your displacement vector delta r, which is the blue one there, you can see is actually literally the change in displacement vectors, or the difference in the two displacement vectors. So it's literally equal to r2, the final displacement vector, minus r1. Because if you go and try with the rphet, okay, and you take r1, right, and turn it upside down and stick it at the end of r2, you'll discover you in fact get that blue vector. And I think I'll let you guys try that. Okay, so how do you determine the direction of delta r? It always points from the starting point to the end point. Okay, or you draw your two vectors, r1 and r2, or figure out their components, and you calculate r2 minus r1. Okay, it's a vector subtraction, exactly. Okay, so then once you know what r is, delta r is your displacement vector, you can figure out your velocity vector, because the average velocity is just the displacement vector divided by the time elapsed, and it has components. Vx, the velocity in the x direction is the displacement in the x direction divided by time elapsed, and the velocity in the y is displacement in the y direction divided by the time elapsed. Just like we saw already for one-dimensional motion, you just now do it separately in each of the two directions, right? So you've got the x component of your velocity is just what we did before, and then the y component, similar idea along the y. Okay. And then we do our acceleration vector. And just like we saw last time, the average acceleration is the change in velocity divided by the time elapsed. Okay, and you get change in velocity, just like we saw before, it's the final velocity minus the initial velocity. And in this case, to get the two components of the acceleration vector, okay, so these are the components of the average acceleration vector. I didn't stick little averages in here, but I should have, because these are average quantities. Okay, though if we do constant acceleration, the average is equal to the instantaneous. But basically, you can see that the x acceleration you get from the change in the x components, and the y acceleration you get from the change in the y components of the velocity. So it's basically, you can treat them completely independently of each other, the x and the y. That's one of the nice things. So it's basically, when you get to 2 dimensions, you just have to do it twice instead of once. Okay, so we've got 2 more minutes here, so we should have time to do this. So let's look at a specific example of calculating an average acceleration. Okay, so we know, like we just saw, average acceleration is the change in the velocity, which is a difference between two vectors, a vector subtraction, divided by time elapsed. Now, time elapsed is just a scalar, it's a number. Okay, so it's not going to change the direction of the vector, it's just going to change its size. All right, so say this is our two velocity vectors. Say v1 points between the x and the y axes like this, whereas v2 points below the x-axis like this. And you want to figure out which way does the acceleration point. Well, to figure out which way the acceleration points, you got to do vector subtraction. We have to do v2 minus v1. So this is what it would look like. Okay, so we've got v2 minus v1. Okay, and we draw, so I basically drew my v2, I reversed my v1, make it minus v1, I stuck it at the tail, right, I stuck the tail of v minus v1 at the tip of v2, I might get my v2 minus v1. And so this is the direction of the average acceleration, because the average acceleration points in the same direction always as v2 minus v1. And just one more quick thing, because we're basically out of time. If you look at that vector v2 minus v1, you'll see it's the vector that points from the tip of the first velocity to the tip of the second velocity, v2. Why does that make sense? Well, it makes sense because if delta v is the change in velocity as a vector. So if you started with velocity 1, v1, and you added the change, you should get to v2, right? Basically, delta v tells you how much the velocity changed between the two times. So it makes sense right? That if you take v1, the red vector there, add delta v, you should get v2. Okay, so, and now I've got some, so, well, no, v2 is, yeah, v2 is the sum of v1 plus delta v. Okay. Why are we subtracting? Okay, so we're subtracting here. Okay, basically, if you look at this vector equation down here, v1 plus delta v equals v2. If you were to subtract v1 from both sides, then you would get delta v equals v2 minus v1. Delta v is in the direction of average acceleration. It's not the same. If you want to get the actual average acceleration, you got to divide by the time elapsed. Okay. So other questions here? Yeah, you may have to label these things yourself sometime, yes. Right, average acceleration is the slope of the velocity time graph. Right, exactly. And in the case of 2 dimensions, you would have a graph for both the x and the y components separately. So average acceleration is defined to be the second velocity, the final velocity minus the initial velocity divided by the time elapsed. So you're always going to be subtracting v1 from v2. Okay? So you're subtracting v1 from v2, that way around. Okay? So I'm going to stop the recording now, but I can